Yes, unfortunately, I don't speak Latvian well enough yet to give a whole talk in Latvian, but maybe next time. We'll see. So yeah, I'm Jake. I'm from Australia. Been here for 9 months working at Nordigen Solutions. Before that, I was working in high-frequency trading at Optiver, and before that, I was at Dolby Laboratories and then IBM in Australia. I put on here Jake Sebastian-Jones BSc because what's important here is some missing other letters in that I don't have a master's or a PhD, and we're talking about science later on in this presentation, and you should all know that actually I don't know anything about science. I've got a lowly bachelor's in computer science, not a maths or physics degree, so just ignore everything I'm about to tell you about physics. Cool. What's Nordigen? I'll try and just do this stuff briefly, but you know, it seems to be the thing to do, talk about the company you work for. So, whoa, that does not look good. Fuck it. So, Nordigen, let's go back to that, it's distracting me. Nordigen is a transactions categorization company primarily. We take raw transaction data and we apply essentially tags to it to mark what kind of transaction this is. For example, giving to charity or going to the brothel. This would be two different ends of the spectrum of activities you could tag with data. But I would, man, these things really don't stretch nicely. Yeah, so then there's some quotes from customers about how this transaction tagging we do increases the, what do they exactly say? Improves the accuracy of identifying risk-critical insights by 40%, whatever. Point is that this activity that we do makes some predictions that our customer is trying to make about something in the world more accurate. And that's what I want to talk about today. Yes, good. Don't bother with pictures, they don't work. So these are the kind of things, problems we address: processing documents, detecting tampering, fraud, distinguishing different kinds of income. The main part of it is categorizing transactions, identifying behavior patterns, and currently the main application of this whole stack is assessing credit risk. Cool. But I would like to say that all of this can be summarized, can be re-expressed as what we're really doing is reducing entropy. Does that make sense to anyone? Hopefully, no. Because I want to explain to you why the thing that Nordigen does is reduce entropy. Let's see why these things don't stretch, because there's some cool animations later that I want to show you. I'll worry about it when we get to it. Alright, okay. Let me just fuck around with like why this doesn't look nice. Because I want it to look nice. Maybe I can just change my resolution to something that looks nicer. What do you reckon? I know, because it's mirrored, and then I can just that can look better. Looks like nothing at all. Better. All right. Computer science degree in action. Reducing entropy. Cool. So in order to explain to you why what Nordigen does is reduce entropy, we have to go to Vienna in the 19th century. Very beautiful city. Most people, when they see this slide in my presentation, people showed before, think that it's Riga, because Riga is equally as beautiful an international city as Vienna. So why are we going to Vienna? We're going to meet Ludwig Boltzmann, who in the 19th century in Vienna was very interested in why certain processes in the natural world are irreversible. Why, if I take a piece of paper and set fire to it and get heat and ashes and all of this stuff, isn't there an anti-fire that I can set anti-fire to the ashes and it turns back into a sheet of paper? That's a cool thing to be interested in. So he theorized that it was because at a molecular level that the particles in this piece of paper that you're burning, kind of like balls in a billiards table, that when you set fire to it, they become more and more and more jumbled up, and as with balls on a table, as you hit them around, they just become more and more randomly distributed, and they will never become more and more ordered. It's not in their nature to become more ordered. It's in their nature to become more random. And so this was one of the precursors to the whole concept of thermodynamic entropy, and they're inventing thermodynamics at this time. It's really cool. This is the bit where you have to remember I'm not a physicist or a mathematician. Boom, setting fire to something. Lovely, nicely ordered piece of paper. And what doesn't happen, what is very unnatural and you wouldn't expect to happen, is this. Yeah, so the reason that looks creepy or unnatural or wrong is because it's violating this principle of entropy, that things tend towards disorder and chaos and randomness, and they don't, through natural processes, just go back nicely into their box. How long do you want to keep watching this for? Cool, so now let's go to New Jersey in the 1940s and meet someone else. So, thermodynamics is a thing now, and, bombing people into a puddle of bleed on the floor is about to happen soon, and science has advanced. And one of the sciences which is about to be born is information theory. So Claude Shannon, if you haven't heard of Boltzmann, I'm sure some of you at least have heard of Claude Shannon, because basically every electronics or engineering degree at some point you'll encounter his theories about encoding information, communicating information. So here's the father of information theory. His alma mater is MIT, worked at Bell Labs, and he went to high school at Gaylord High School, which you should know. He wrote a famous paper on the mathematical theory of communication. And he was interested in how do you encode messages efficiently? And through this process, he was thinking about what is information? What are you talking about? What do you need to encode? So basically, he came up with a theory that what information is the opposite of randomness. It's the opposite of Boltzmann's molecular chaos. What information is the ability to predict exactly where something is at any time. Whereas with these billiard balls, what is the chaos of these balls? The point is that you don't know where any particular one of them is on the table. And as this process goes on, it becomes more and more random. Cool. Does that make sense that I missed that? Does someone want to ask any questions, or have I lost anyone at that point about why it is that information is the opposite of entropy? Maybe? Let's, yeah, maybe this example will make it clear. So, information is the reduction in uncertainty, it's the opposite of entropy. Good. So imagine that your mission is to navigate in a maze. Your default sort of strategy would be to move randomly. So you take random turns, you move more and more randomly, and eventually you would arrive at your destination, yeah? Say take the same maze, and you've got a map, you've got directions to the goal. You can just navigate directly to the goal, and you save a lot of time. The difference in the time taken between moving randomly and moving directly to the goal is a kind of indirect measurement of information. So it's this concept of order in opposition to randomness that you can measure in the world by, by certainty. Is that all right? Let's move on and see if it, we can come back in the summary, see if that makes sense. Good. Yeah. So this algorithm is a good example because this algorithm is operating with only partial information, so it has to move semi-randomly. All it knows is that the walls don't move around. So it can, if the walls moved around, it would have to move randomly because it couldn't make these decisions here. This is it gathering information until it comes up with a certainty about where the exit is. Cool.
This is called robot vacuum cleaner works.
By gathering information about your house, yeah. Okay, so informally, there's this concept of entropy that's regarded as a tendency towards disorder. In a thermodynamic sense, that's not entirely accurate, but for normal people like computer science people, we can think of it that way. Information and entropy are opposites, and once we move into information theory, it's kind of formally defined that way. We can just define information as a reduction in uncertainty, or a reduction in randomness, or an ability to know exactly where, when we rack these balls, here I know exactly where each of those balls is on the table. There's no uncertainty. There's order. It's not chaotic. Great. So the more entropy is more uncertainty, more information is less uncertainty, and the critical point is that as you reduce uncertainty, you can make accurate predictions. So I can predict with 100% accuracy where all these balls are. I rack them into a triangle, navigating through a maze. Once you have the map, you can navigate straight to the exit. Information is a reduction in uncertainty. Another point that's important is that data by itself doesn't reduce uncertainty. So I can give you a huge matrix of values. Data is just values. You can have more and more and more values without becoming more certain about anything in the world. Yeah? Cool. FinTech, finance. Should be music or something at this point. So how is this relevant to finance, or why have I wasted your time with an amateurish explanation of entropy and information and data and probably confused you more than necessary? Well, because finance, money and economies are complex network systems with this huge tendency towards entropy and randomness and chaos. So much so that stock prices are modeled using these chaotic processes like Brownian motion. This is, in options pricing, this is the model of stock prices. It looks a lot like balls bashing around on a table, but on a huge scale of a whole economy of all the people in the world interacting, creating this chaos. But obviously, in the stock market, for example, if you can make accurate predictions, you can make a lot of money. It's like, a small child can understand the value of being able to make accurate predictions. And the reason that I've been using up your time talking about entropy and information is that these accurate predictions, which are so valuable in the financial world, accurate predictions, that's a synonym for reduced uncertainty. And reduced uncertainty is the information science definition of information. So this bringing order out of chaos is a fundamentally valuable thing that many institutions are willing to pay you money for if you can develop a system that can create information. Cool. So how do we do that at Nordigen? Basically, we take raw data, raw transaction data, we put it through a whole series of processes, each one of which reduces the entropy, creates more certainty, creates value, and then we actually monetize at most of the points on this scale. So obviously, the further you go down, the more information there is, the more valuable it is. the more it's going to cost you to query these APIs. But see some examples. Okay, this is an example of a bank transaction. It's a line in your bank statement. So we can clean out this high entropy part of the string here. We can get rid of some of the duplicates. We can remove the special characters, remove this keyword here, and come out with this phrase here. So this really interesting question from a sort of scientific perspective, whether this string here has more information or this string. Does anyone want to comment on that, or anyone have a strong opinion about which of these two things contains more information?
Yeah.
Yes.
First one.
Very interesting.
From the set theory, because first one and blue second, so we can possibly have less information than the second one.
That's interesting. Not a mathematician. From my perspective, when we see that information is a reduction in uncertainty, it depends on whether you can make more accurate predictions with the first than the second. So there are some, like Google and other big companies, people are developing technologies where you can dump raw data in and extract information or make predictions with raw data. But these are very rare and cutting-edge technologies. So I think probably in theory, you're probably correct that removing anything at all reduces the potential information has been reduced. But the actual information is better if you remove things which are going to decrease the accuracy of your predictions. So in our technology, when we first clean the transactions to remove certain types of repetition or certain characters, we actually can make more accurate predictions. And so as far as our prediction models are concerned, this has more information than this because it's less uncertain. Cool. So it's actually, yeah, it's possible to measure that directly because you can build a model, make a prediction. Then I can change the way that I'm pre-processing or cleaning my input data, rerun my models. My models are making more accurate predictions, then I've added information. And if they're making less accurate predictions, then I've made it more chaotic and more random and reduced the information. So if you can do this process well, this is something that you can monetize. So this is a really simple, this is just string manipulation, you know, this is, yes?
Where do you get sample?
This is from our production data with this thing changed.
Sample on which to get.
To test your, so we have a whole load of our own data. Do you mean where would you get data if you wanted to start your own business doing this? Or,
obviously.
Yeah. So a lot of our training data is provided to us by new clients that maybe in a new market that we want to enter. They want us to train our algorithms, and they provide us their own data. They provide us training sets to use to train our models. Cool. So yeah, as far as our models are concerned, deleting these things may actually improve the, might increase the information. Okay, so after we clean transactions, we want to apply categories to them. So this casino cafe, which I found on Google, is that a casino or is it a cafe? There's a cafe in a casino. There's a uncertainty here. And where I find this whole information theory, information entropy concept interesting is that you don't actually have to look it up on Facebook as I did in this case. Or you don't have to go there and investigate. Is this a casino? Is it a cafe? I can just create two different schemas. In one I'll tag it as casino, in another I'll tag it as cafe. Then I'll look at my predictions that I'm making based off of that data. If my predictions are more accurate if I call it a casino, it's a casino. Another way of seeing that is actually that the labels are completely arbitrary. I could just tag them all as A, B, C, D, E, F, G. The fact that I'm tagging it as casino or not isn't relevant to the prediction at all. They're just arbitrary categories. Cool. Okay. So we do a level of cleaning, we do categorization, then we do have to do another sort of round of cleaning, which is what do we do with outliers, what do we do with null values, and again, there's a simple test to see whether, these are like common strategies in statistics of what you do with missing values. Maybe use a random one, use a common one. But there's a test to see whether if I take all of my outliers and replace them with a random value or replace them with the mean, have I increased the entropy or have I increased the information in my that I'm putting through my pipeline? Well, are my predictions more accurate? If they're more accurate, then I have more information.
How do you know that they are more accurate?
So we have a, for credit scoring, we have training sets of people's account history and whether or not they defaulted on a loan. And then we use standard statistical techniques to backtest these algorithms on whether it would have predicted that these people did or didn't default on their loans.
So in some cases, for the casino cafe, so if I'm most likely to pay back that money credit that you give to me, so it's most likely it will be used as a cafe option at the casino.
These are human intuitions, which are often fairly accurate, but often but sometimes not. So the thing they'll really tell you is just looking at your output data. So you have to do a lot of back testing and a lot of experimentation to see if what you're doing is improving it, or if you're just, what are you doing to the pool table? Are you taking all the balls and gathering them in and ordering them nicely, or are you just putting your hand in and like changing it without increasing the information content? Cool. Boom. So then we do feature selection, which is another layer of increasing the information. So that you have all of these data points, and you have to choose which ones you're going to input into your statistical models. Some of that we use human brains. Some of it we use algorithms. So this would be also known as machine learning. Often using fewer features is better and more predictive than using a lot. So we end up with thousands and thousands of lines of people's bank statements, or companies' whole financial histories when they need to be credit scored, and we come up with basically a vector of usually far fewer than 100 values that are used as an input into the statistical models. So again, whilst I think probably as a mathematical principle, the potential information has been reduced because we've deleted so much, the pragmatic information is a lot higher in this vector of 100 key values than in the dump of raw data. Difficult. So then we do statistical modeling. We use a bunch of different models. Different models are more appropriate for different kinds of predictions and in different scenarios. We combine the models, and ultimately you come out with a single score, which is a prediction of whether or not someone is going to repay their loan or not. And this value here, you know, if you're a bank or a lender that wants to give someone a loan, and I can tell them what this value is, that's something that they want to pay for. They don't want to pay for a big dump. Well, I've got heaps of data about this guy. Here, have megabytes of characters and make your decision based off of that. Well, it doesn't help because it's just a random, like where in all of those thousands of individual UTF-8 encoded characters is the thing that tells me whether to give them a loan. It's this number which tells you whether or not to give them a loan and what the margins should be, this is information. Is there anything else to say? Yeah, there's just the same thing, but smaller and harder to read. Okay, so there's a concept of information and it implies accurate predictions. To create information, you have to sort of bring order to a chaotic environment. In finance, information is a really valuable commodity, and that doesn't mean that you have to be Google and come up with a algorithm for just ingesting huge amounts of raw data and doing something really cutting-edge genius. You can do something like some string manipulations and reduce the chaos to some extent, and there'll be someone out there that was willing to pay for that service. Then you can obviously amplify that and apply more and more intelligence, instruct more and more information, and the more information you create, the more people in the financial world are willing to pay you for it. Yeah. Hopefully that was more interesting and less confusing than it could have been. Does anyone have any questions? Yes.
How to avoid overfitting?
Yeah, so some of that is by making sure that you don't have outliers included in your data sets, because overfitting is often fitting to outliers. So, and that can be eliminating even reasonably uncommon values. So maybe that's even say that so you're only testing people in a particular city. Maybe you want to include information about gambling at a particular place, but only say 5% of all of these people have ever had a single transaction at this place, and then maybe you're at risk there of overfitting to include that as a feature. But those are standard statistical techniques of how you avoid overfitting and what percentage of your data set should have a particular feature, have a value for a feature before you include it.
But do you take these decisions manually?
Some of it is using, like the human brain is one of these information processing systems. It just takes this random electromagnetic signaling and turns it into accurate predictions. You know, I know which direction to turn my head to look at you. I don't have to choose randomly. So for human beings to look at the data and make a informed decision is leveraging a very powerful information processing machine. So some of it is done manually. Certainly these first steps of, okay, so we're scoring someone for a loan. Probably how much money they earn is a relevant factor in whether or not they can afford the loan. Whether they've defaulted on loans before, that's probably another important factor. So it's not an arbitrary decision, it's using your intuition, which is coming out of your intelligence. Yes.
So it's quite difficult to assess the quality of the credit risk scoring, because for a bank, probably the number that you give them is coming from black box, right? They don't know exactly how you got to 0.89. So do you have any form of service level agreement with your customers? So how do they actually assess whether those numbers make sense?
Yes. In fact, for most of the large customers, we do challenger tests, usually on their premises with their own data, and the sort of sales call is, hey, we've got this amazing thing, it's going to improve your ability to make predictions. Bullshit, you do. No, seriously, we do. And then, well, come and show us then. So we go on site, we explain what our intention is, what sort of, they give us benchmarks of, okay, if you meet this level, that's what we would consider a successful test. And then either we're running just our system or we run it in direct opposition to our competitors, and that's how that works.
this servers, one of the options how to kind of prove is to run against like historical data.
Say that again?
So let's take for example historical data. So
Yes.
you have customers who had the loan and they paid or not paid.
Yeah.
So you go back, you can do the analysis on them and see what was the outcome and if you can more or less kind of fit to the actual situation.
Exactly, exactly. And the banks and other institutions that we are providing these services for usually have very particular goals, or they have particular things that they're trying to predict, and that's the test data that they use when we run these tests. Yeah.
How much do you rely on Bayesian statistics and hidden models, and how much is it ML?
Well, what I was trying to get at with this multi-layered sort of information processing is that some of our customers aren't paying for any modeling at all. They're paying for the categorization or the cleaning stages. Obviously, it doesn't cost them as much because it's not as rich. It's kind of like processing minerals. Like if you have an iron ore mine, you can sell raw. Iron ore is basically just dirt. Like it's just, you can dig the earth, put it on a ship and send it to China and people will pay for it. Or you can go through many different layers of enrichment through to selling the steel yourself. And that's kind of like what we're doing. Some people we're just doing the very minimum enrichment, like selling the iron ore, and other people we're doing the modeling for. I would say mostly it's split between people who are just interested in categorization and want to do their own modeling and scoring, and then people who want the features, want us to decide which are the critical features, and then they include those features into their models.
Do you ever go back and validate your scores? Like you have given score this, they got a loan and they defaulted. Did you investigate why?
So we never approving anyone's loans, or we don't offer any financial services. So so that activity does happen, but it happens. Our customers are constantly retesting, and we have to keep updating our feature selection and our models. And we do that in collaboration. There's a feedback loop with our customers and their ongoing success rate.
Do you focus on B2C only or B2B as well?
It's B2B is our exclusive business case.
No, but I mean scoring. Is it scoring for private persons or scoring for factoring?
I'm not sure the exact percentage of our customers' use case. Its majority of it is private individuals, but we do a lot of scoring our businesses as well.
Oh, yeah.
Cool. This, yeah.